Hey there, math fans. Dr. Andy Lovelace. This is a quick motivation video. Right now, we're starting to study curves in 3D in my Calculus 3 course. A while back, I made a video about how I was going to ask some tennis questions, which I hope to get back to. And at the time, I made a 3D visual of a tennis court, an accurate visual. And eventually, I'm hoping to teach a class where we talk about that a little bit. And explore and go to the tennis courts. If I can convince, my department just said, no, I can't teach it. But if I can convince someone else to allow me to teach a course where we get to do tennis and do math at the same time, I'll be excited to do it. But I made this model where I was able to tweak numbers. This is without assuming air resistance in other spin and other factors. This is just a parabola in 3D thing. And I played around with it. The reason I'm mentioning it here is I always think of this as an example. I think of also many situations like this, but 3D has a lot of space. And what I mean by that is just think of this example. If you've never played tennis before a match, you warm up and then usually you hit serves. Oftentimes when you're playing doubles, you'll have people serving crossways. So one person will be on this side serving. They'll be standing somewhere here. They'll be serving, hopefully getting a few in. And at the same time, the other two people playing doubles are serving and warming up. So they're crossing paths. I've been playing tennis for about 40 years. I've played, I don't know how many matches each year. I've warmed up many times. I've watched people warm up. Despite the fact that you have these people warming up in this diagonal fashion, well, person's hitting balls this way, a person's hitting balls this way. I had never, ever, ever seen the balls hit each other, even though they often were traveling at the same time, until a couple months ago. I was warming up, a bunch of old guys warming up like me, and the tennis balls hit each other. It was amazing. We had to stop and talk about it. The point of that is to say, I always think of this as it's very rare for two objects in 3D to intersect. But we just hit them just right. Because not only do the paths have to cross, that's probably happened many times, they have to be there at the same time. That's a collision thing. Okay, so that was this game. So if I had this tennis ball going here, and let's animate it and send time forward here. Just a moment. So let's send time forward. There they go. Slow it down a little bit. Whatever's happened, let's say the green ball is fixed and this person is trying to hit it. And they're lucky enough that the other person across the way always hits it at the exact same starting time in the exact same warm up. And we're going to adjust to try to hit it perfectly. And you can just see how hard it is. So I've made it so I can tweak the yellow one. Let's see if we can hit it. This is just motivation. Watch my other video where I actually talk about solving, how you take the equations, how you combine. And in that I talk about if you're just studying the paths intersecting, that's an easier question, but you have to use different parameters. So let's try to make the paths intersect first. See how close we can get. We're getting pretty close here to the paths intersecting. So let's tweak our numbers a little bit. Maybe I can, ooh, that looks like it hit. Yeah, I did it. So those now look like they hit. So now the next thing, so if your goal is to find the paths intersecting, we've done it, but they don't get there at the same time. That's why it's so important, I talk about in class, of using a different parameter for each one if your goal is to study the paths. Because the paths do intersect now. If your goal is to study the tennis balls intersecting, that's an added challenge. And the trick is the first person, this yellow person serving from the yellow side, is going to have to serve a little later. They're going to need to use a different parameter. So I don't have that set up here. I'd have to tell that person, you have to wait a moment before you serve if you want to match up. Or you'd have to tell the person doing the green. So let's play that game. I'm going to change the time for the person hitting the green tennis ball. and I'm going to add it. Give me just a moment. I wasn't quite ready for this. And now I'm going to show them. Okay, so then I go, what time does the green one need to be there? Oops, it's too it's too picky. So 0.2, 0.3, 0.4, 0.65 seconds. So now the other person would have to adjust. So they're there. Now they do hit, but they're not there at the same time. So the difference in time, now we'll have to figure that out. Let's see and take a look. The yellow one gets there. Pause it. And point. My hand is too shaky. Old man. Okay, in 0.8 seconds. It gets there. So the person serving yellow has to wait. What did I say? 8. Okay, 0.15 seconds to serve. And then the balls will collide. So that's why it's so hard, but that emphasizes this point. I tell the students that if you have two curves in 3D that are random, very unlikely they hit. It's somewhat more likely that their paths cross, but that's not necessarily at the same time. And so if you're studying curves in 3D, you need to use different parameters for each one, unless you actually are studying collision. Then it's okay to use the same parameter. But a good rule of thumb is to use different parameters for each one. Don't assume they were all served at the same time if you're studying the paths. So I think that's a good I hope that's a motivation for you. It's an example I've always used. I just have never actually shown it here. And I'm happy to tell this story that it did happen once in 40 years that I saw two people warming up diagonal wise. I wasn't hitting either one. Unfortunately, I was not involved. I was on the court, but I was receiving one of the serves, and they did it. Success. All right. Thanks for listening.